So the next talk will be given by Alexander Armbruster, and he will tell us about approximation algorithms for non-preemptive throughput maximization. So Alexander, the floor is yours.
Thanks. So this is joint work with Fabrizio, Antoine, and Andreas. And I generally like to eat stuff from the bakery. And stuff I like, for example, are croissants, bread, bagels, or cheesecake. And sometimes this stuff is hard to get. For example, I was kind of disappointed with the breakfast this morning. So the only option you have in this case is you have to bake it yourself. And if you want to do this, and let's say you have organized some brunch and you want to bake all of this, you run into an issue because you only have one oven, and all of this stuff needs to get into the oven at some point. And like things you have to keep in mind when you plan this is that, well, each of these things take a different amount of time in the oven. And they actually also should be finished at slightly different times. So the croissants should be finished first because you want to eat them first. Cake is kind of the dessert thing, so it's fine if it's done later. And you also don't want to start them at arbitrary moments. So I don't wake up before 8 o'clock, so I won't bake anything before 8 o'clock, for example, and the dough for the bagels and the cheesecake first and so on. So you have these kind of requirements. And if you formalize this problem, you end up with a problem called maximum throughput, where you have given a set of jobs, each job indicated by like one color, and each job is given by a processing time and a time window, which is like the window between its release time and its deadline. And the goal is to schedule these jobs on one machine. And a schedule might start with the red job, then do the purple one, then do this light blue one, and finish with the green one. So as you can see, you are not allowed to preempt the job, which makes sense if you think about baking, because you can't preempt cake if it's already in the oven. And the objective is to maximize the number of scheduled jobs. You could also imagine a weighted version where jobs have weights, but we are only focused on the number of jobs. This problem is well studied, and I'm interested in approximation algorithms for it. So first of all, the problem is strongly NP hard, and that's also all known about any kind of hardness. Then for quite some time, there's an E over E minus 1 approximation algorithm by Chuzoi. And like 9 years ago, there's also an improvement by a tiny amount to like 1.55. And so our result is an improvement to 4 over 3 in this time. And also we were able to improve our approximation ratio further if we are allowed to use pseudo-polynomial time instead of polynomial time. So some side remarks. First of all of these algorithms are randomized. And also you actually can extend them to multiple machines. So if you want to do this, you can do this. And maybe as a side remark, if you have many machines, then the problem actually gets easier. So Imli and Moseley showed that if the number of machines is sufficiently large, you can achieve an approximation factor of 1 plus epsilon. So the really interesting case if you have one is if you have one machine or you have like a very few number of them. So in the remaining time, I want to give you an idea of what our algorithm is and like kind of on how our analysis works. But before we come to that, we have to, like, I will give you an overview over the approach from Chuzoi et al. And the idea there is as follows. So first, they compute a block decomposition. And with that, I mean that you look at the time interval and you partition it into intervals, which are called blocks, which might look something like this, indicated by these black bars. And this decomposition has very nice properties. So there should be, there is an optimal, like a near optimal solution of prime, so scheduling almost as many jobs as opt, such that first of all, there shouldn't be any jobs overlapping these block boundaries. So these crossed out jobs can't exist in opt prime. And also there is an upper bound of k jobs that can be scheduled in each block. So in this example up there, there are at most 2 jobs in each block. And the computation of this block decomposition is non-trivial. And we also use it only as a black box, so I won't go into detail about how it works. If we have this block decomposition, the remaining algorithm is as follows. So the idea is that you look at some configurations, which is just like a set of jobs that can be scheduled within one of these blocks. And because each block can schedule at most k jobs, the number of configurations is like n to the order k, so it's just a polynomial. And this means that we can easily set up a configuration LP that looks something like this. So you have a variable for each configuration, and you have two type of constraints. The first one says that for each block, you only have one configuration. And the second constraint says that for each job, it's scheduled in at most one configuration. Now, given this LP, well, since it has a polynomial number of variables and constraints, we can compute an optimal solution. Now we can use randomized rounding. And the idea is that for each block independently, we sample a configuration according to the LP solution we just did. If you do this, you might end up with something like there at the bottom. So for each block, you got a configuration. But as you can see, like the red job is sampled in 3 different configurations, and the blue job is sampled in 2. So what do? Well, you just remove the ones that were sampled multiple times. So you end up with this schedule of 4 jobs. And if you do the maths, you can show that a job is included in the solution with like probability e minus 1 over e times its LP contribution, which results in this approximation factor of e over e minus 1. So our goal was to improve this approximation factor to 4 over 3. And for that, well, we kind of use a very similar approach. So we also start with a block decomposition and there's kind of as a block box, but we have to modify it, and I won't go into detail what kind of modifications we make there. For the purpose of this talk, just think about what we just had as well. Now, the issue was that we were kind of unlucky because we got one job 3 times and another one 2 times. So in some sense, we got 7 jobs, but we have too many duplicates, which kind of costed a lot in the approximation factor. So the idea is that instead of thinking about the sampled things as jobs, we think of them as just a slot. We have like 7 slots, and each slot can fit one job. Now the question is just which job do you put in which slot? And for that, you can compute a maximum matching. So for example, this blue job would go into these 2 slots. It can't go into the slots on the left because its time window doesn't go there. And it can't go into the other 2 slots because its processing time is too long. So the last step is just to compute this maximum matching between the jobs and the slots. And this might look something like this in our example. So as you can see, we were able to fill all slots, which is great. That's also already a whole algorithm. So the algorithm is fairly simple. You just use the box and solve this configuration LP and just do this matching step at the end. So in this example, it was kind of clear that this matching step helped. I will also try to give you an idea why it helps in general. So for that, for simplicity, assume that all time windows are the same, like in this example, and also assume that they span like a large number of these blocks. Now the idea is to use harmonic grouping. And like the height of one, like you have one rectangle for each job, and the height is kind of its contribution to the LP. And if you have this, you can partition the jobs into groups like this. So according to their processing time, the largest one in one group, the second largest second group, and so on, such that you have like order of 1 divided by epsilon many groups. And each group should contribute about the same amount to the LP. So this gives you these groups. And given these groups, you can ask the question, how many slots do you get from each of these groups? And because we have these configurations, and these configurations are fairly small, now you can use concentration bounds, like Chernoff bounds, to argue that the number of slots you get from the first group is about the height of this stack of jobs there. And the same is true for the other groups. So with sufficiently high probability, we actually know how many slots from each group we will get if we do this rounding. And now we can use the slots we got from the first group and fill them with jobs from the second group. And the slots from the second group can be filled with jobs from the third group and so on. So if you do this, the only empty slots are the slots from the last group. Because it's only 1 over epsilon many groups, means that actually we essentially filled all of the slots. And this means that, well, we get a known plus epsilon approximation because the number of slots we get in expectation is exactly the LP objective. So this kind of idea shows that you get a 1 plus epsilon approximation under these circumstances. The idea for to prove the 4/3 is, of course, a bit more technical, but it's still kind of the idea to use this harmonic grouping step for like large areas for jobs. So now I'll talk a bit about the 5/4 ideas. So let's take a step back again and think about what actually makes a schedule feasible. So there are kind of two properties. The first one is that at any time there is only one job scheduled. The second property is that each job is scheduled at most once. If you have these two properties, this kind of gives you a feasible schedule. And our approach so far was to independently sample a configuration for each block. And if you do this, this directly implies that at most one job is scheduled at any times, because that's just how our configuration worked. And then the second property is kind of not so clear to achieve, and that's why we had this matching idea, or the previous algorithms just deleted duplicates, so that then we had somehow lose our approximation factor in ensuring the second part. Now, the idea for the 5/4 approximation algorithm is to use the opposite approach, which is similar to the approach also used by IMNI and Moseley. So instead of sampling a configuration, we completely forget that we had these configurations. We just independently assign each job to a block. If we do this, it's pretty clear that each job is scheduled at most once because we assign it only to one block. But it's not so clear how the jobs assigned to a block can actually fit into this block. So it's not so clear how to actually ensure that we can schedule these jobs non-overlappingly. Sadly, the talk is not so long, so I won't go into a lot more detail about how this rounding works. But the overall idea now is that we have these two kind of rounding algorithms, and we just solve the LP once, and then use both rounding algorithms and just take the better of the two solutions. So to compare these algorithms, there are two types of jobs we have to consider. There are local jobs, which are like jobs whose time window is contained in a block. And there are the other ones at the bottom whose time window is not contained in a block. So it contains a block boundary. And the for the configuration sampling algorithm we had at the beginning, if you have non-local jobs, you just get the approximation ratio. But if you have local jobs, the algorithm is actually better, because the issue kind of with this algorithm is that you sample a job multiple times and then it doesn't really fit anymore. But for local jobs, this can't happen. You can't sample it multiple times because there's only one block where you can sample it. So actually, if you only have local jobs, this configuration sampling idea would give you a 1 approximation. For this job sampling algorithm, it's kind of opposite. So actually, we have to discard all of the local jobs there, because if you have local jobs, it's very unclear how to put them into a block. If you don't have local jobs, you can actually set up a very easy greedy algorithm that schedules all of them if it's possible to schedule all of them. So for that reason, we have to discard all the local jobs in this setting. And for the non-local jobs, we can actually then ensure that we get like a factor of 1 minus epsilon for them. So if we use these two rounding algorithms and use just the better of the two results, this gives you the 5/4 approximation factor. Maybe as a side remark, for the second algorithm, we actually need a different, to get this factor of 1 minus epsilon at the bottom right, we actually need slightly different blocks again. So we actually need blocks with more than a constant number of jobs. So this means that we can't solve the LP in this straightforward way we did before, because we no longer have a polynomial number of variables and so on. So this makes this also where the pseudo-polynomial running comes from, because we then have to solve the dual via a separation oracle and stuff like this. But yeah, that's where the pseudo-polynomial running time comes from. All right, so we obtained this 4/3 approximation algorithm in polynomial time, and to 5/4 in pseudo-polynomial time. That's all I wanted to say. Thanks for your attention.
Thank you. Do we have any questions for Alexander? So maybe I will ask one. Is this known to be APX hard?
No, there's nothing known about hard, like strongly NP hardness is known, but no APX hardness from all we know there.
And what's the main reason why you didn't present the PTAS today?
So it's difficult to describe, but somehow the main issue is that like if you kind of do this randomized rounding, jobs can be like the difficult jobs are the jobs that are either scheduled at the complete left end of the time window or at the complete right end. And it's kind of difficult because that's like at different places in the LP and you don't really have control. That's kind of the difficult part. So the middle is not really the issue. The issue is really the left and the right end point of that time.
I see. Any other question in the meantime? Okay, if not, then let's thank Alexander again.